In this video, we're going to look how the number system has developed over the last couple of thousand years. Now in school today, we're used to using negative numbers, irrational numbers like the root of 2 or e or pi, but it's not always been this way. I mean, our early ancestors would have still needed to count. However, they would have used like simple tally marks like this. Not even like this, for instance, they might have just had just single scratches in a bone or a bit of bark to count maybe the number of cattle they have in a herd and so on. But quite quickly, they developed the need to write this stuff down. Okay, and we started with our basic counting numbers or the natural numbers. Okay, so this N symbol here with a double line through the middle is notation for the set of counting numbers, our positive counting numbers. So I'll just write a few elements in that set. So we have the number 1, 2, 3, and so on. And this set consists of all the positive whole numbers. So we might include in here the number 507, the number 1 million and 2. For instance, okay, so these are all positive whole numbers, and we can classify those as the natural numbers. Okay, now as the human race developed, there became a need to record larger and larger numbers. And these natural numbers, yes, they're okay for recording large positive numbers. But during this time, we introduced the idea of place value. Now, this wasn't always the case. People developed symbols for all sorts of numbers. The Babylonians, for instance, had 60 different symbols for 60 different digits. Now, place value was very important, and actually it revolutionized maths a little bit with this number 0, which actually was first written down in India by an Indian mathematician of the name Brahmagupta. Now, along with 0, Brahmagupta also introduced the notion of negative numbers, which at first they were received with kind of contempt by mathematicians all over the world. However, due to a need to record debt, when someone owed you some money, and when someone, for instance, owed you 7 mangoes or something like that, they quickly became commonplace. And that leads us to our next set of numbers, which is the integers. Okay, so integers are a set of numbers in their own right, which include negative numbers, they include 0, and they include all of the whole natural numbers that we had before, so your 1, 2, 3, and so on. Okay, so these are still whole numbers, so they're still numbers like -4 or -57. But we don't have any fractions or anything yet. Okay, now with these numbers, we can still do mathematics like usual. We can still add them together. We can subtract them. Okay, that makes sense. Getting rid of debt, for instance, that made sense to people. But there was some quite big discussions about what it means to multiply negative numbers. And I think you'll remember actually the first time that you came across this. What does it mean to multiply two negative numbers together? Your teacher probably had quite a hard time trying to explain to you why a minus number times by a minus number equals a positive number. And really it took a while for the human race and mathematicians to accept this fact, that a negative number multiplied by a negative number was a positive number. And once mathematicians became happy with these ideas, it just became commonplace to use them and just use this idea. There is still an issue actually with the number 0, and it comes with division, and still we're a bit uneasy with the idea of dividing by 0. And actually we've just kind of come to conclude that actually that isn't allowed. We've not allowed that to happen in mathematics. So we've realised now that by 700 AD, mathematicians had rules and were able to use negative numbers, positive numbers, and 0, and were just able to add them, subtract them, multiply them, divide them, and use them as the same way as people were using natural numbers before. Okay, so these were our integers denoted with this Z with a double line through it. Okay, now before that, actually, I mean, back in Egyptian times, back in ancient Greece, people were using fractions, just positive fractions. But now, after 700 AD, we were able to use negative fractions as well. Okay, um, so this is all encompassed by this set of rational numbers, denoted with this letter Q with the double lines around the outside. Now we use the letter Q because a fraction is a quotient of two numbers. So Q is a letter which is used to represent the quotient. Now I'm going to write this in set builder notation and I'll explain it as I go through. So the set of rational numbers are numbers of the form A over B, okay, such that A and B are both integers. Okay, so A and B are members of the integers. And also, this denominator B is not allowed to be equal to 0. Okay, so what types of numbers can we put in here? Okay, so we've got any fraction really. So we've got something like a quarter that can go there because 1 and 4 are both integers and the denominator isn't 0. We could have something like minus 7 over 6. Okay, that's fine. Although it's top heavy, that doesn't matter. It can be written as a fraction. The number 4, okay, because although that doesn't look like it's in this form, we can always write that as 4 over 1, okay. But there's other numbers here which are a little bit in disguise. For instance, you might have the number 0.341, okay. Now the number 0.341 can be written as a fraction. It can be written as 341 over 1,000, okay. So although it doesn't look like a fraction to start with, this number here is also a rational number. And where we've got to be very careful is where we start using recurring decimals like 0.2 recurring. Okay, because although it's a recurring decimal and it goes on forever, as long as a decimal has this repeating pattern, it can be written as a fraction. So actually 0.2 recurring can be written as 2/9, so it can be classified itself as a rational number. Okay, so far what we've got are most of the numbers that we've used so far in mathematics. We've got our counting numbers, we've got our negative numbers and 0, and we've got our fractions. But we've also seen a couple of other numbers, the likes of the square root of 2, pi, e, the golden ratio. If you don't know what that is, it's the square root of 5 plus 1 over 2. Okay, so these numbers here we know cannot be written as fractions where the top and bottom are integers. Okay, so they can be written as fractions like this. However, there's an irrational part here on the top with the square root of 5. Now, real numbers are really any number on our number line. Okay, so if we've got our number line like this with 0 in the middle, 1 here, 2 here, 3 here, we've also got negative numbers like -1, -2. Okay, now if we just had whole numbers like this, just had integers, then we'll know there'll be loads of gaps. And we don't really want gaps in this line. Okay, so then we started introducing these rational numbers. Okay, so we could have things like a quarter. Okay, so we know that a quarter would go just about here. We would have the number, say 2.5. Okay, so 2.5 would go here. But there would still be loads of little holes in our number line, and we're not really allowed that if this is to be one continuous line. So we needed a number, a type of number here, which kind of explains where these numbers like the square root of 2, pi, they also need to be part of our number system. And that kind of leads us to our final set of numbers, which is the real numbers. Now, real numbers are really any number, as I've mentioned, that can be put on our number line, just to make this one continuous line. There's no gaps now. Wherever we choose, we'll be able to describe that number either as a fraction, as a rational number, or as some other number like root 2, pi, e, and so on. Okay, so that's numbers where the decimal representation has no repeated pattern and it goes on forever. Okay, so these numbers are all of the numbers that we have used throughout GCSE, throughout A level, in fact, throughout all of our lives. We've been happy knowing that these are all of the numbers that we could possibly need. But then every once in a while, mathematicians stumble across problems which get them to reevaluate their idea of a number. And this has happened a few times in history so far. First of all, it came around 700 AD, as I've mentioned before, where the Egyptians and Brahmagupta came up with negative numbers and zero. Secondly, back in Pythagorean times, it was thought that the only numbers that existed were numbers that could be written as nice proportions of integers. So the rational numbers they were happy with, but numbers like root 2, they really didn't like them at all. In fact, it was treason to suggest that these numbers existed. Now, legend has it that a guy called Hippasus came up with this problem, that if we had a square of side length 1, what number would represent the length of this diagonal? Okay, now Pythagoras and his group of Pythagoreans tried to find a fraction for the solution to this, but just however hard they tried to find this number, they always failed. And actually, legend has it that Hippasus was put to death. Okay, he was executed for suggesting that this number root 2 could even exist. Now, obviously, mathematicians have come to accept this fact later on, and it's no longer treason. I mean, if you write root 2 down in your A levels, no one's going to execute you for that fact. But you may have realised that there are times in mathematics where these numbers have failed us. And one of those times is when we start to use the quadratic equation. So we get x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And we may have realised that at times we've ended up with this number under the square root sign being negative, and we weren't able to evaluate it. So, for instance, the square root of negative 4 or the square root of negative 81. Now, there's nowhere on our number line to put those, okay? So what this means is, can you find a number that multiplies by itself to get negative 4? Now, obviously, if we choose a positive number, we know that a positive number times a positive number gives us a positive number. And if we chose a negative number, we've got a negative number times a negative number is also a positive number. So if these numbers here, if they did exist, and if we were to use them in mathematics, the question is, where would they go? Okay, they can't go on this number line. They're not a real number. So where would they go? Okay, and that's a question that mathematicians had. And they really didn't look at this in too much detail until the 1500s, where a guy called Cardano realized that he needed to use one of these numbers to solve a problem. And since then, actually, mathematicians weren't happy with these numbers at all. Some went as far as saying they were meaningless and completely nonsense. And that led to a man called Descartes. Okay, you might have heard of him, René Descartes, calling these numbers imaginary. Okay, they were completely nonsense and they didn't exist. Now we're coming to the end of this video, but in videos to come, in the next few videos, we're going to see that although they've been called imaginary, which is a bit of a ridiculous name now, it's kind of unfortunate that they've been given that name. Imaginary numbers, along with a wider group called the complex numbers, are actually very, very useful. And in recent years, they have been used in many a proof to advance mathematics even further and to the point that we are today. Okay, so in the next couple of videos, we're going to look at complex numbers in much more detail and hopefully give you a better idea of these numbers outside of the real numbers. Okay, thank you for listening, and goodbye.